Okay, and the way we do it, a predicate would be given to you involving integers or positive integers. So you prove that predicate or a statement for the initial step, n equal to 1 or any other numbers. And then you assume that this machine or predicate is okay for a specific number, okay, fixed k, then you prove the next step. So you go from k to k plus 1. If it's going to be true, then you refer to the fact that this property can be happen only if you're working with the natural numbers. So the result is going to be your predicate is true for all positive integers. Okay, that's the action of the induction. So now what we are going to do, we are going to use that method in order to produce something. Okay, a mathematical structure, if you like. This type of argument is going to be called, we say the method is called inductively defined sets. So you are going to introduce a set of whatever it is, objects, numbers, characters, using a kind of induction format. Okay, in your book, they call it recursively defined or recursive definition, but we use two expressions. Inductively would be much, much better. Okay, so this is a very interesting section, 5.9. Okay, that you are going to use it quite a lot. So as is in your book, they call it a recursive. Okay, that's it. Recursive definitions. Okay, but it's much more than the definition really, or recursively defined set. The other expression that I like, and it's mostly common in mathematics, we call this procedure inductively. Okay, inductively defined sets. We're going to define a set, okay, a procedure by a machine, if you like. Okay, this is going to be the way we do it. So what does it mean, this type of definitions? You see, so what I want to do, I want to construct a building, if you like. So what I need a foundation. Okay, whatever we want to do, you need a foundation to build your house on that foundation. So the first step is going to be the foundation. We call it basic steps. Since you want to grow something, we refer to this basic step as seeds. Okay, so just tell you what I'm going to do. So I need a foundation. As soon as you give me a foundation, I will plan how I'm going to make or to construct my building. To make my building, so what I do based on that foundation, I'm going to construct the first floor. So when I'm done with the first floor, based on the first floor, I'm going to have my second floor. Then based on the second floor, I've already got the experience from the going from 1 to 2, I go from 2 to 3. So then I have a machine. This machine automatically will give me all the other part of my buildings. So I need a foundation and I need an instruction to give to machine that the machine automatically will do the job for me. Okay, so I need the following. So we say that the recursive, okay, recursive definitions, if you like, or inductively define definitions of a set of a procedure. A set always need the following. Consists of, okay, the following 3 steps. Consists of three distinct step, or we call them clauses. Okay, you need the following to construct some, the basic one. The first one. The first one is the foundation. We call it the basic. Okay, the basic step or basic clause. I like to call it seeds. If you want to grow something, you need a seed. Okay. So what is going to be this? This would establish, okay, this first part, it, if you like, establishes what? Establishes that a certain object, remember you want to make a set. Certain objects are in your set, are in the set. You see, if you want to make a set, you need something to start with. If you want to buy something, you need money. Okay, so first thing to do, as soon as you're given something to start with, we say, oh, so my set is not empty. So I have something to start with. Okay, so therefore, because you cannot build anything on an empty set. So therefore, the set is not empty. So this clause would guarantee that your set is not empty. Okay, this part. So this part of the definition, I just emphasize again. It's the same thing. This part of the definition, if you like, specifies my expressions, okay, the seeds. So the one that I started is going to be the seeds of the set. Of the set, of course, from that I can grow something. From which the elements of the set, the elements of the set, the element of the sets are going to be produced or generated. Generated using a machine, using methods. Methods given in the next step, given in the next step. You see, that's the first part. Okay, you want to build something, you need something. That's it, foundation. The seeds. So you have the seed you want to grow. Now how are we going to do it? Okay, that's a big step. And then when you want to do the problem, you have to identify the basic step for us first. Okay, so we have a plan, if you like. We have a plan and we have the investment, the seeds. So how are we going to do it? Second part. You have to give us a roadmap. What's the roadmap? The roadmap is called the inductive clause. In your book, they call it recursive clause. Inductive one is going to be something that you'll be able to repeat it over and over and over. So this is the method that we need. It establishes the base in which elements elements of the set can be produced, can be combined This is an instruction to combine to produce new one. okay, to produce new elements. New elements from the old one of the set. See, that's going to be 1. So you have the seats, for example, as I told you, go to the first floor. When you get the first floor, then you have a formula. Based whatever you did for the first floor, you are going to get to the second floor. So the first floor is going to be the old one. This second floor is going to be the new one. Then you go to the new one. You introduce the old one. And you introduce another one if you like. So my interpretation is that, you see, the old elements are going to be what? Are going to be the parent. Okay, the old one is going to be a parent of the new elements, which are going to be children of the new objects, which is going to be the child, if you like, or object, the child. Okay. So the parent would produce the children, the new one. Then the children becomes the parent of the next step, and it's just going on forever. Okay. So for by the inductive step, this is the way we're going to go ahead. Do it over and over and over. Okay. So we start with the seeds. Seeds produce new elements. So the old element is going to be the parents, the new one is going to be the children. The children becomes the parents again, introduce the children, produce the children, children, parents, you can keep going on forever. Okay, any question? But we have to stop somewhere. Step 3. Step 3, this is the one we call it the terminal clause. The terminal. The terminal clause, you are going to put some, or sometimes in your book they call it restriction. Okay, restriction. Restriction is going to be when you form all the objects of your sets, you are going to have go back and check to see, make sure that you are not going to have anything that is going to be produced out of his instruction. So you shouldn't have any member from outside of this definition that you're going to have. Okay, so every element in the set should be either a seed or one of these procedures that you did over here. Okay, it's just double check if you like. So it asserts, okay, asserts that unless an object, okay, an object can be shown, to be a member of the set, to be a member member of the set by applying the basic and inductive clauses a finite number of the time. A finite number of times the object is not a member of your set. The object is not a member of your set, a member of the set. So this means anything in your set should come from this procedure. You cannot have anything outside of your sets if you like. So if I pick one element of your set, you are going to show me that this element is either a basic clause, or you can do a couple of operations. You repeat your inductive clauses to arrive at that elements. Okay, just guarantee that the result is coming from here. Okay, let's give you an example to see how we're going to operate. Any question, get some idea of what we're going to do is a procedure that we do it. We give a formula to the machine will do it for you. Okay, the machine will replace the n by 1, by 2, by 3, and operate it recursively, going back to get these numbers. Okay, so let's give an example to see how we're going to construct it. And there is something else that you can do with these sets. Then I explain that one too. Okay, so get used to expression. We have the basic. This is going to be 1. We use the basic step to show that we can form a set. Set is not empty. Then you have to check this machine a couple of times for us on the examples, and you get the sets that you are going to be interested in. Okay, let me just give you an example to see, to get the idea. Those famous examples that I told you, counterexample that constructed by envelope, in linear algebra, he just used these methods to get it. This is the example. So the problems are easy, but you have to write it down correctly to get the points on the set, on the test. There you are. You see, suppose the set S, we give you the instruction, you are going to form the set for us. Suppose that the set S, okay, is defined recursively or inductively. I use both expression, recursively, as follows. We have to give you the basic step and the instruction roadmap. You do it for us. Okay, so what is the basic step? I go with the B and the I. In your book, they go with the B and the R. It doesn't matter. The basic clause, the fact is that the radical 2 is in S. Remember, you need this one to make sure that your set is not empty. So you start with the radical 2. The next step, I call it I. In your book, they call it R. It doesn't matter. R or I. Instruction. What's the instruction? The instruction is that if X is in S, then a square root of 2 plus X is also in S. That's the instruction. So what we'd like you to do is we'd like you to list, let's say 4 elements. 4 elements of the set. We may ask for the 4 or 5 of the set S. That's it. So you do just at least a couple of times just to show us, and then you can find all the 4 elements. Okay, are you ready? This is the way you do it, solution. Step 1, you have to show that this set is not empty. You get help from the B. B is the seed, remember? So you claim that by B, radical 2 is in S. And so your set is not empty. That's it. Therefore, to start with, you have a set containing 1 element, radical 2. That's a step 1. Any question? So you have the seed. This is the parent. Now you have to use this instruction to produce a child, if you like. So how are you going to do it? Read this one. If X is in S, okay, you say, oh, note that X equal to the radical 2, now you call this one X, is in S, because you have it, is in S. Now we apply the second part, okay, and by the machine, by I, the result, S square root of 2 plus X is also in S, okay, the square root of 2 plus X, which is the square root of 2, okay, plus radical 2, is going to be is in S. You see, the parent produces children. So what we have so far, so S is equal to radical 2, one element, the other one is the square root of 2 plus radical 2. So this is your S so far. And now we can continue. Okay, take this one as a, so this would be a new parent. This new parent, so we repeat it, say X equal to the 2 plus radical 2 is in S. So by I, you get the next one. What is the next one? 2 plus radical X, 2 plus, okay, 2 plus X, I write it down here. 2 plus X would be what now? Would be 2 plus radical 2 plus radical 2 is in S. So basically your set is going to be, therefore, what do you have? There you are. S is equal to the first one radical 2, the second one 2 plus radical 2, the next one 2 plus radical 2 plus radical 2, and the fourth one is going to be what? 2 plus 2 plus, okay, so we get to this one, 2 plus radical 2. And of course we have more elements, but you've been asked only for 4 elements. That's it. Any question? On the test, if you want to write 4 or 5, 6 elements, you have to do this operation for us at least twice. Then you can list all the other elements. If this operation ends up with somewhere, it is going to be the case. Then you have to list all the members for us. Okay, so it's going to be very easy procedure, but it must be, okay, done nicely. It's induction, like induction. So we start with the basic step to prove that there is a seed. So that's the first step that you have to check so that it's not an empty set. Then you replace the X by the seed that you have, whatever formula you have. That give you a child. So your set would be now radical 2 and the new child. This now is going to be a parent. You replace the X by this one and repeat the formula again. You do it over and over and over, and that gives you the elements that you're going to be interested in. 4 elements. Any question? Interesting procedure. Okay, let's have another one. To get the idea, then we go with the one on the practice one. Example. Get this one. Define. Okay, define the set X recursively. Okay, define it recursively. Inductively, discuss it as follows. What's the instruction? The basic part. The basic part is that the 0 is in X. So this set is not empty. What's the instruction? Inductive, or I just write R so that you know that they are the same. Recursive one is if X is in X, then X plus 2 is also in X. So that's one. They ask for 5 elements. List 5 elements. 5 elements in X or of X. Again, don't just list 5 elements for us. You have to tell us how you did it. Are you ready? This is it. Start by the basic part. By B, 0 is in X. 0 is in X. And so X is not empty. Therefore, so far, X is this set, the foundation. So this is your seed. Start to grow. What are we going to do? If X is in X, take the X to be 0. 0 is in X, so X plus 2. 0 plus 2, which is going to be 2. 2 would be in X. Okay, so you explain that X equal to the 0 is in X. Now, by recursive part, X plus 2, which is 0 plus 2, 2 is in X. So what's going to be your X so far? 0 and 2. Okay, repeat it again. It's going to be a new parent. X equal to 2 is in X, again, by R, X plus 2, which is going to be 2 plus 2 equal to 4, is in X. You see, 2 step. Now you can list the other one. You know that you replace the 4 that give you 4 plus 2. So now you can claim that. Therefore, what's going to be member of the sets? The first member 0. You add the 2, the second number. We add another 2, the third. You add another 2, 6, 8, etc. Done. This is the way you do it on the test. You have to repeat this procedure twice to show us that your machine is working. Okay, and you get the result right away. Okay, any question? Very easy procedure.
One question.
Yes.
The recursive function x plus 2, is that going to be given? Like for
Yes.
okay.
Yeah, that you have to be given a machine.
Okay.
Yeah, always you have to, you have to be given, otherwise you can't do it. Yeah, the first part and the second part will be given to you. Otherwise we can't do it. Remember, you need a seed. You need a seed and those clauses, okay? Let's see what is different about this one. This one is, you see they give you this set. Let X be, okay, let X be the set of integer. The set of integers. Okay, the set of integers defined. Okay, defined recursively. As follows. Let's see what is this one. You see the basic part. The basic part is 4 and 6 4 and 6 are in X. They give it 2 elements in the set. That's better. Now what's the machine formula? The formula is this one. If X and Y are in X, you see are in X, then X plus Y is also in X. Okay, 2 elements. So they ask you to list, okay, list all elements. All elements. List all elements in X. Okay, all elements in X or of X that are less than 20. That are less than 20. Okay, are you ready? Solution. Again, by basic part, you have 4 and 6 in X, so we already got 2 elements. By basic part, you have to explain it, remember. 4 and 6 are in X, so X is not empty, and X so far is 4 and 6. Okay, we always apply the basic part to show that there is something. Now what's a machine? Machine is that if X and the Y are in X, then X plus Y is in X. So you already got 2 elements, X equal to 4 and X equal to 6. So we can apply these two and the machine, okay? So say that X equal to, okay, this is going to be the case. X equal to 4 and Y equal to the 6 are in, okay, are in X. So apply the recursive part, add them together. You see, X plus Y, X plus Y is going to be 4 plus 6, which is 10, is in X. You can have more possibilities. You see, 4 plus 4, which is 8, is in X. They didn't say X and the Y are going to be different. They say X and Y. You can have one more. 6 plus 6, 12 is in X. So what do you have so far? Your X would be what? 4, 6, 10. 4, 6, 10, 8, and 12. You see, you got lots of numbers here. Any question? They ask for all the members less than 20. Could you give us more elements now? To get less than 20. You have lots of new, okay, new parents if you like. So you can get the combination of the parents to get all the members which are going to be less than 20. I say just similarly. X equal to, so what I have so far, I have 4, 6, 8, 10, 12. Any suggestion? More elements. Remember your instruction. If x and the y is in x, then x plus y is going to be in x.
6 plus 8. 6 plus 8 is equal to 14.
So we can have the 14. Yes, you are right. Remember, you must be less than 20. Okay, anything else?
We can do 8 plus 8 to the 16.
8 plus 8 equal to the 16. You are right.
8 plus 10 is equal to 18.
8 plus 10, yes, 18. Anything else?
And finally, 10 plus 10 is equal to 20.
But they asked for the less
Oh,
than.
less than 20. Yeah,
Okay.
sorry.
So
No, that's it.
seems to be that's it, yes? That's it. Because they asked for less than 20. Less than 20, this is all the possibility that you can have to be less than 20. Okay, any question? So we just check it up to the 12. Okay, so you have to add this to get the new members. Since they ask for less than 20, so we just, stop 6 and 8 would be 14. We can have more, you see, 10 and 12 would be 22, but we cannot have the 22. So sometimes they put some kind of a restriction, then you have to, you have to stop to get those restrictions done. Okay, any question? Now, there is one more steps that you can do with this type of ideas, and this is the one that we're going to be interested in. What is that? You see, we have, when we list these members, we'll find out these members are interesting. Look at this one, the one that I put over here. Let's go back. Look at this one. The instruction was this number. Instruction was 0 is in x. If x is in x, then x plus 2 is in x. We list only 5 elements. Look at these elements that we have. Can you see something interesting about these elements? These numbers?
Sure, they're all even.
They're all even. Yes, they're all even. We know that it's going on forever, but we can prove that without writing any other elements. We can prove that every element of this set is an even number. Every element of this set is going to be an even number. How are we going to prove it? Induction. That induction is very nice one. We call it, we call it a structural induction. So what's going to be a structural induction? Remember, each induction would have what? Would have 2 steps. Basic step, and remember, inductive steps. What was the basic step of the integral in the induction? The basic step is, remember, P0 must be correct if you like. So P in this case is the property that you want to prove. You want to prove that every element in this set is an even number. So the basic step of this induction would be that the basic element would have this property. When you say P of 0 is correct. So the P is that every element in X must be an even number. So the basic step is the basic element is an even number? Yes, it's done. So the basic step of this induction is going to be the fact that the basic element would have the property that you are looking for. It's done. What's going to be the next step? Remember the next step? The next step is if k is an integer. If pk is true, you prove pk plus 1 is true. Remember, you fix one step and you do the next step. So what we're going to do in this case is going to be quite interesting. You are going to prove that if I pick an element in X, that satisfies the property P. What is the property P? Remember, pk is true. Property P is that if X is an even number. So that pk step that we have induction would be replaced with the fact that the x is in x is an even number. Then remember, you have to prove the next step. pk plus 1 is true, but your next step is the child. So you prove that if x is an even number, then x plus 2 is also even. That's it. So you assume the pk and you prove pk plus 1. If you prove these two steps, we say, oh, in structural induction, every element in X is going to be even number. Quite interesting and nice procedure really for the induction that we're going to use. Okay, this type of induction is going to be called a structural induction. So basically, what's a structural induction? You have the property you want to prove. You prove that that property is true for the basic element. That would be your P0 if you like. Then you assume that it's true for the X, it's assumed for a parent, and you prove it for the children. So the parent children, that is going to be true all the time. Okay, I write it down so that we can get this one too. Okay, it's quite interesting, and maybe this is the only one that you may use in your fields in structural induction, not the others. Okay, it's a remark. What is, some people think that they don't need to prove this type of ideas, but that's the fun part of these arguments. What is in structural induction? I promise you that we are not going to give you any more induction in this course. This is the last one. And the easiest one. So that's it. We apply. Okay, we apply in structural induction. In structural induction. Okay, to show that. Show that the elements in a set in an inductively defined set X has the property P, whatever you want to do. Okay, I like the one that I did. So you have to assume, remember in the case of the ordinary induction, we say, oh, what is the Pn? So you have to write something. You say P is the fact that I want to prove that every element in the X in the set is an even number. You call it P. Then this is it. In the basic step, basic step B of your induction, B. Okay, B of the induction, we prove. Okay, we prove that what? We prove that the element in the basic step, of X, remember seeds, has the property P, property P. That's it. Whatever you want to prove, you prove it for the basic element. This is P1. This is the P0 that we usually go for it. Okay, Now the step that you assume that the pk is true, you want to prove that it is true for pk plus 1. Then in the inductive step, I of the induction, we prove what? We prove that. There you are. You go for we assume it for the parent, we prove it for the children. Okay, in this case, we prove that if an arbitrary is like, any k, an arbitrary element, say x. Okay, this is going to be what? This is going to be a parent. Has the property P, then the children. Okay, then the element, generated from X, a child, would have the same property. Has the property P. That's it. That's exactly, interpretation of the fact that we say that if pk is true, then pk plus 1 is true. It's quite a nice one. It does give you, better, some kind of understanding of how we do the business in mathematics, really. It's the same thing, but you put it into the new format. That's why we like it. To give you, hope that you get it and you'll be able to use it in future. Any question? I'm preparing a talk for the coming seminars. Someone they asked me for a journal talk. You know that because I teach discrete mathematics and at the same time I teach calculus. So when you do discrete mathematics, it's quite different from calculus, because in calculus we know that we use real numbers, over here integers. But some of the idea of the calculus can be generalized to this discrete mathematics, especially the derivative. So I read this article before, of course, but I just recently, since I've been asked for the talk, I just put them together. Give a definition of a kind that you use in definition of derivative of a function in the case of this type of a structure. But you don't have this type of function in discrete mathematics. What you do have are these sequences, recursively defined sequence. So I'm just using the same idea like the power rule. Remember, in algebra or in calculus, derivative of x to the n is nx to the n minus 1. But you can put them into these type of ideas. If I get time, before the end of the course, I give you just a little bit of that, so that you will see how important are these type of ideas, recursively defined. And you get something quite interesting. Maybe they are not going to be used as we use it in calculus, but mathematically it would be nice to give this type of idea. I show you later on, because it's very much related to what we are going to do here. Okay, so let's get one example of how we're going to prove it for us on the test. Okay, we give you one example of this one. Okay, and so I give you one quickly, then I go back to the one that you have in your practice one. Okay, let's do the one that we did over here. Okay, so example is going to be this one. Okay, So suppose a set X set is given to you. Okay, the one that we talk about it. I go with this one. Maybe that's also in your, okay. Yeah, I do this one, then I go with the one that we have. Okay, suppose we define a set of this format. Define. This is a good one because we have a basic, the recursive step is interesting. Define a set. Let's do one quickly, then we go back. A set X. Define a set X of integers. Okay, integers recursively as follows. Okay, I do the one that we did, I do one something quick, then I go to your, you see the one that we did was the fact that the 0 is in X. Okay, and the recursive part was if X is in X, if X is in X, then X plus 2 is also in X. Okay, so what we'd like to do is we'd like to prove by induction. By induction that every element of X is an even integer, if you like, or even number. That's it. You don't have to list the members for us for this one, okay? So if we ask, if we want to list the elements, we give you this question separately. So the solution is going to be, are you ready? You don't need to list the elements, just for your information. If you like, and note that we did it before. The first element is 0, then you add the 2. You see, these are the ones that you have. Okay, so this is the way you're going to organize it. You have to organize that property P that we talk about it. Okay, so 1 should prove. 1 should prove that every number, every element in X is even. Okay, so that is going to be, that is property P, if you like. Just want you to compare it so that you know it. For the basic part, you show that the basic element in this set is an even number. You see, the basic part of the induction. The basic part is that the 0 is an even number. Even number. So that's the basic part. You have to show that the basic element of the set would have the property P. Done. Any question? Inductive parts. You assume one parent, X in X, would have the property P, and you show that his child would have the same property, and you're done. You remember, you assume the PK and you prove PK plus 1. So for the inductive part, you assume that. Assume that X is in X and is even. So what's the definition of the even number? So there is a K such that x is equal to the 2k. Bring the children. The children is x plus 2. That would imply that the x plus 2 is 2k plus 2. You know that you factor out the 2, that give you k plus 1. You call this one k1, that give you 2k1. So x plus 2 is going to be 2k1. So x plus 2 is even. That's it. So you assume a parent x is even, you have to form the children, x plus 2. Now you say by in structural induction. We got it. Every element in x is even. And you're done. See, very easy procedure. Quite interesting. To get it. And make sure to write it down. You made a miss. Some of you made a miss when they write this one. What they do, they start with the x plus 2, which is wrong. They assume that x plus 2 is even, then they want to prove x is even number. No. Remember, start with the parent, you get the children. So you must assume x is in x is an even number. Then you prove x plus 2, which is a child. Not starting with the child getting to the parent. Okay, otherwise it's going to be a safe problem. That is 5.9. Let's do any question? As you can see, it's a quite interesting one and we don't want to miss it for this quiz. So we give you one of them on the quiz and I'm going to quickly check it for you. This is going to be the case. So we get 2 questions from this one on this quiz and 2 on the next test and 1 on the final. This induction would be repeated on the final. So that is a practice quiz number 3. I will post the solution of all of them for you, but I like to do this instructional one that I talk about it now. Okay, you have, let me just do, I started at the end. I do problem number 9 first of this practice one. Explain this procedure, but otherwise, you'll be given 2 questions on this format that we're going to have. Okay, so this is a practice. I post the solution of the rest for you by tonight. I have a class by in-person class at the university up to the 6 o'clock. But when I get back, I post it for you. Okay, so practice quiz number 3. Okay, I explained the number 9. Number 9, a set is defined as follows. Okay, defined a set S recursively as follows. It's similar to one problem of your book, and it's a very popular problem. The basic part is that the 0 is in S. You see this notation belongs to S. We did it before, but this means 0 is in S. I'm going to use this notation on this test, but we have it in chapter 6, but it doesn't matter. Recursive part is that the fact that if X is in S, then X plus 3 is in S, and X minus 3 is in S. See the definition of the sets. They ask you to list 6 elements, list 6 elements of the set S and prove. If you don't ask for the elements, you're not going to list it on the test. List the 6 elements of the set and prove that every element is divisible by 3. Divisibility is, is just a popular format for these type of problems. By 3, by 5, by 2. Okay, are you ready? 6 elements. Show us 2 elements, list the others. Solution. First part. Basic. 0 is in S. By basic, 0 is in S. So this means S is not empty. And S has 1 element, 0. Take this 0 into the recursive one, make more. X equal to the 0 is in S by the recursive part, X plus 3 and X minus 3. X minus 3, which is 0 minus 3, is a negative 3, is in S, and X plus 3, which is equal to the 0 plus 3, equal to 3, is in S. So what do you have so far? 0, negative 3, 3. Okay, similarly, S is equal to 0, negative 3, 3. Give us more elements. Your machine is whatever X is, X plus 3, X minus 3. More element.
Negative 6 and 6.
Negative 6, 3 and 3. Negative 6, yes.
6.
6.
Negative 9
Negative 9.
and 9.
1, 2. Yeah.
Oh, right.
Okay. So they ask for the 6th element and you're done. Okay, question? So if you've been asked, we just did the elements. So that's the first part. Any question? Now we want to prove the induction. As you can see, all of them are divisible by 3. So inductive part, start with this expression that 1 should. You have to introduce property P, remember. 1 should prove that every element in S is divisible by 3. This is property P. Property P for a reference. Okay. So what we are going to do is the basic step. So the basic step is going to be, the basic step is your basic element mass should have this property. Basic element is 0. 0 is divisible by 3. 0 is divisible by 3. Done. That's the basic step. Inductive part, you are going to pick one parent with the property P, and you show that their children would have the same property. One parent with the property. You say that, suppose X is in S and X is divisible. Divisible by what? Divisible by 3. Okay, you must assume this one. And then you go for the x plus 3 and x minus 3. Write the divisibility formula. This means there is a k such that x is equal to what? 3k. That's the parent. Who is the children? The children. X plus 3 is going to be what? 3k plus 3. You factor out the 3, k plus 1. You call it k1, that give it 3k1. So x plus 3, the children would be divisible by the 3. And x minus 3 is going to be 3k minus 3, which is going to be 3 times k minus 1. You may call this one 3k2. So that's it. So x plus 3, the children, and x minus 3 are also divisible by 3. Divisible by 3. You see, you assume a parent with the same property and you prove that the children would have the same property here. Assume the pk, you prove pk plus 1. So by induction or structural induction, by induction, that's it. Every element, every number or every element S is divisible by 3. And you're done. See, very nice method. Any question? But be careful. You see, I look by this one when I want to grade it. You must start with the, okay, you must start with parent. Some people, they don't say anything. They go, say, no. Remember, you assume that the pk and you prove pk plus 1. So you have to assume this one. Okay, you assume this one first, okay, then you go to the x plus 3, x minus. No, not from, they do the other way around. They assume that x plus 3 equal to the 3k, and then they subtract the 3, and they prove that x is also divisible by. No, it's not. This is not going to be done, because your procedure of the induction is what? You assume the pk, you go to the pk plus 1. So your machine is, this is the machine is going to be operated, okay? So it's not going to be anything complicated, but the logic must be correct. Just make sure your logic is correct. Okay, so this is the inductive part. You have a couple of more. They are not going to be difficult. You can check it for yourself. Okay, I give you the number 5 is easy question. Okay, we give you 2 questions on this one. It's algebra. Remember, recursively we define, just to make sure that you don't make a mistake identifying this one. And this is algebra. 2 questions would be given at 5. And we call it a linear, so that we are not going to miss it. No induction is needed for this one. Linear recurrence relation. It's the one that you have to use, you form the characteristic equation, then you have 2 solutions, repeated solution or distinct one. You want to solve these relations, okay? So this is going to be the first one. an is equal to the 7 an minus 1 minus 12 an minus 2, with the condition that the a0 is 0 and the a1 is 1. Okay, remember we change it into the characteristic equation. So the characteristic equation would be start with the r squared equal to whatever it is here, 7 times r minus 12. That's it. The power is 2, 1, r to the 0. R to the 0 is 1. That's why you don't have it. Okay, move it to one side. Carefully solve this equation, factoring all the time. Just make sure the factors are correct. R minus 4, R minus 3 equal to the 0. You have two solutions. You call it R1 and R2. See? They are different. When they are different, your solution is AN equal to C1 R1 to the N, C2 R2 to the N. You substitute AN equal to the C1 4 to the N plus C2 3 to the N. This is true for N equal to the 0, 1, 2 forever. But you have initial condition. Initial condition is A0 is 0, A1 is 1. You have to substitute, get the C1 and the C2. A0 equal to the 0. You replace N by 0. So it's going to be 0 equal to the C1, 4 to the 0, C2, 3 to the 0. So that gives you C1 plus C2 equal to the 0. This is one equation. Any question? Apply the next one. A1 is equal to 1. You replace the N by 1 in the equation. A1, 1 equal to C1 times 4, C2 times 3. So you have 4C1, 3C2 equal to 1. Put them together, find the C1 and the C2. So what we have? C1 plus C2 equal to the 0. 4C1, 3C2 equal to 1. Substitution method, elimination method, you can use whatever you like. So I multiply this one by -3 to eliminate the C2. Negative C1 plus 3C2, 0. 4C1, 3C2, 1. Add. Okay, that's a negative, of course. So these two would cancel out. So that gives you C1 equal to 1. Okay, that gives you C1 equal to 1. You go back and substitute here. So 1 plus C2 equal to the 0. So C2 would be -1. So the general solution AN is equal to C1 is 1. So that gives you 4 to the N. C2 is -1 minus 3 to the N equal to the 0, 1, 2, etc. So this gives you the general solution. Any question? So it's not going to be a difficult problem, but some people, they make a mistake here. Carefully, move it to the other side. Okay, check. Make sure you get it all right. And at the end, you get this. Okay, it's going to be one question. Any question? Just quickly give you the second possibility of this one. So we are done with 2 questions. Yes, question.
So do we have to do it exactly how you did it for the full points?
What do you mean?
Like usually, so when you get to C1 plus C2 equals 0, I usually I would do like C1 equals -C2.
Yeah, I said substitution method, no problem.
Okay.
No problem. No, I mean, I taught you once. No. It depends on the problem. Yeah, I said substitution or addition, both of them would be fine. Okay, any question? Don't try, since some people, they use matrices or something. No, it can be done. No, you can use either. Okay, so let me quickly give you the case 2 so that you know how to operate these 2 problems. And it's going to be repeated even on the final, okay? Because that was one section. So the second possibility is this one. Okay, -9, Bn minus 2. And the condition is B0 is 1 and the B1 is 3. Okay. So the solution is going to be, so we start with the R squared. 6r minus 9. You start with the highest power, which is a square, then 6 times r minus 9r to the 0. Move to one side. Okay, if you factor it, that give r minus 3 times r minus 3 equal to the 0. So it's a repeated solution. So our solution are the same. See, r1 is equal to the r2 is equal to 3. So just call it r. And in this case, you know that the Bn is what? C1 r to the n is one solution. C2 n times r to the n, or nr to the n, is the other solution. N, 0, 1, 2, etc. Just make sure you use the proper one, or the repeated one. Substitute. So that gives C1 3 to the n plus C2n 3 to the n. Okay, but you have a initial condition. B0 is 1, B1 is 3. Check this initial condition in this form. Okay, B0 equal to the 1. Means you replace the n by 0. So this would be 1 equal to the C1 3 to the 0. The other part would be 0 because n. So this is going to be simply 3 times 1. 3 to the 0 is 1, so it's going to be C1. So C1 is 1. Okay, question. B1 equal to 3. So n equal to 1, we start with the 3. N equal to 1 here. C1 times 3 plus C2 times 3. Okay, we got the 3 all over the places. So what we have is a 3C1 plus 3C2 equal to 3. You can simplify by 3. That's it. But you already got the C1. So you substitute. So that 1 plus C2 equal to 1. So C2 would be 0 in this case. So what's the final answer? Bn is equal to just 3 to the n. Or n. You have to give us the n 0, 1, 2, etc. So that gives you the solution to the equation that you're going to have. Okay, so this is not a difficult problem. Make sure don't miss it to get these numbers. There's parts you can do it yourself. Okay, so that's it. I don't have time to give you more. So this is 2 parts. We have the other part is a couple of kind of application problems. It's about the money. Question number 1 and 2. We wanted to write this okay, recursively define equation for us. You put the money in the bank give you 5% interest. It's like algebra. So I put the solutions for you so you can check the other part yourself. Okay, that's it. Any question? So read it carefully. I just wanted to finish this section so that we have, we have one collection all together. So you have time, we practice it, and then we done. We are done with this great chapter, chapter 5. The rest are going to be just, we are going to have different topics, and they are going to be also interesting, but the crunch is done really. That's chapter 5. So we go to the best part of the next case is going to be, we go back to the notion of the relations, and we work on over there. Otherwise, some property of the set, some at the end, counting procedures. We go from one section to the other one topics to the other ones. But you are done with the general topics of discrete mathematics for this course, of course. Okay, that's it. Have a good one. See you on Wednesday for the quiz. You know that as usual, we give you the quiz, enough time to do it on the Canvas, PDF file, etc. Have a good one. Send me an email if you have any question. Bye-bye.
Thank you. See you Wednesday.
Thank you, Professor.